Hello, everyone, and welcome to my channel. This is an educational channel. We look at some great theories of everything and do very deep dives and let you know what they really say and how they can benefit you, because you probably haven't heard of them before. And this is our 437th video on the reciprocal system of theory from Dewey B. Larson. And in 1959, Larson proposed his two fundamental postulates about how the universe operated. And then he elaborated his postulates through a process of deduction to get to his theoretical universe, what his universe would look like if his postulates were correct. And then he compared his theoretical universe with the measured empirical universe of the scientists that they had measured in their labs and compiled in their tables. So, for example, we're looking at his book today called Basic Properties of Matter. This is a book on chemistry, and he looks at many of the basic properties of matter and compares, comes up with equations, derives equations for these basic properties based on his theories, based on his postulates and the derivations thereof. And then he compares the numbers that he gets with the numbers from the scientists from their measurements. So Larson is coming up with answers based on theory alone, and the scientists are measuring it. So you would think that if Larson can basically recreate the numbers that the legacy scientists come up with, that he must be onto something. And so we're going to take a look at that. We are in chapter 4 that is on compressibility. Compressibility is more or less the rate of compression when something is under pressure. Some element or a compound is under pressure. How much of its volume does it lose? So, for example, if you have a shot put, like a ball made out of whatever it's made out of, I don't think it's made out of lead, but I'm not sure what a shot put is made out of. Some kind of hard metal. And you compress that, it's going to compress a lot less than if you have a ball made out of cotton and you try to compress that. So those would presumably have different compressibilities. Now, just to get you a little bit familiar with Larson's universe here, Larson's reciprocal system is also known as the universe of motion. That's because Larson attempts to construct his entire universe upon motion, not matter and not energy or force, but motion. And in particular, Larson is talking about a specific kind of motion that he calls scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You would model that or envision that by having a balloon that you put a bunch of spots on with a magic marker. If you blow up the balloon, all the spots will be moving away from each other. And they won't be moving in any specific direction. Or really, the direction would just be outward. Every dot will be moving away from every other dot. And really, even the locations between the dots will also be moving away from each other. So every dot is moving in every direction. So there is no specific direction assigned to scalar motion. And if you suck in the balloon and it contracts and gets smaller, all of the dots will be moving toward each other. And that's an inward scalar motion. Larson refers to the outward motion as the progression and the inward as gravitation. And then in addition to that, Larson more precisely defines motion over some other theorists who've also had this idea of a universe of motion. Larson defines motion as the relationship between space and time, which sets up a generalized reciprocal relationship between space and time. Motion is a fraction with space or time as the numerator and time or the top half of the fraction, and time or space as the denominator or the bottom half of the fraction. Now, the most basic example that we know of, speed. The bicycle is moving 15 miles per hour. 15 miles of space in 1 hour of time. Space over time. Speed is space over time. And that is, in fact, a fraction with space as the numerator, time as the denominator. And if you decide to double the speed, you can say the bike is now moving 30 miles per hour. But equivalently, you could also say the bike is now moving 15 miles per half hour. That is a reciprocal relationship. You can either multiply the space or you can divide the time. Now, so speed does fit Larson's requirement of a reciprocal relationship between space and time. But Larson spreads that out and generalizes it and says that all scientific phenomena are forms of motion. So including matter and energy and force and acceleration and pressure and temperature and magnetic flux and electric charge and electric current and electrical capacitance and viscosity and fluidity and power. These are all different fractions of with space or time as the numerator and time or space as the denominator, with another caveat that space or time and motion come in up to 3 dimensions, and I would even say possibly more, but at least 3 dimensions. I say more because of Buckminster Fuller and his 4-dimensional kind of geometry, synergetic geometry, which we will also be looking into here coming up fairly shortly, in a couple months. And for example, matter in Larson's system is time to the 3rd power over space to the 3rd power. Energy is simply time over space. So energy is like the inverse of speed. And then another major aspect of Larson's system is the discrete unit postulate. Space, time, and motion come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. This puts into relief the basic idea that you have to get with for the universe of motion. You have to be able to conceive of motion without anything moving. Motion precedes anything that would be moving. And so in Larson's system, this progression, this outward scalar motion, analogous to the surface of an expanding balloon, is moving outward. And that is an omnipresent, eternal, background of the universe. This is always occurring. And it occurs at the rate of 1 unit of space per 1 unit of time, which is also known as the speed of light. So that's what Larson calls the progression of the natural reference system. The natural reference system, as opposed to any kind of humanly contrived reference system that begins with 0 usually. Larson's system begins with 1, just like any reciprocal system begins with 1. And so in this empty universe, or the null point, the 0 point, the neutral point of the universe is outward at the speed of light in all directions. And then what this means is that half the universe is moving slower than the speed of light, and half the universe is moving faster than the speed of light. That half that scientists know nothing about is called the cosmic sector, and the half that we're familiar with, moving slower than the speed of light, is called the material sector. In the material sector, we basically are anchored to what he calls the spatial reference system. And this spatial reference system is basically Euclidean geometry, 3 dimensions of space in a still frame, extension space, XYZ coordinates, but we are progressing through time. We are moving in a scalar manner through time. Time is always getting later and later and later, but in no specific direction. But space is 3-dimensional and still. But if we cross that unit speed boundary and we move into the cosmic sector where all speeds are faster than the speed of light, what we would observe is 3 dimensions of time in a still frame, coordinate time, and we would observe clock space, spatial, a scalar progression of space. Space is always getting farther and farther and farther apart. Okay, so we got the material sector and the cosmic sector, and they are reciprocals of one another. You interchange the roles of space and time when you cross that boundary. Now, within each one of those sectors, there's also another boundary that is like the inside region of each sector. In the material sector, this boundary is established on the unit of space. Space has to be in discrete units, and if you don't have a full unit of space, then you don't have space. You end up getting interactions in less than 1 unit of space, which is about a 1/500,000th of an inch, when you're dealing with atoms and molecules. And so the realm of interaction of atoms and molecules occurs not in space, but in time. Because if it's not in space, then it has to be in time, because the universe is made out of space and time, or motion. And so it has to be one or the other, or both. And if it's not space, then it has to be time. And this occurs then within what he calls the time region. And the time region is, again, the rules are inverted. Once you cross that boundary, that unit space boundary, and move into the time region, then you observe the progression to be going inward and gravitation to be moving outward. And there are more complications there, but we'll just leave it there for now. Now, in the cosmic sector, you have the same thing, except you have the unit of time. Cosmic atoms and cosmic molecules, which we generally call antimatter, are interacting within 1 unit of time, which is approximately 1/6 quadrillionth of a second. And when they do so, they cannot operate in time because there's less than 1 unit of time. So it has to be in space. Larson calls this the space region. And the rules, again, are inverted, and gravitation moves outward, the progression moves inward. And so how do we get matter? Matter is formed from basically the source, which is the progression of the natural reference system, outward at the speed of light in all directions, and reversing that motion First, you end up with two photons, which are oscillating motions or vibratory motions. And there is some dispute as to how those get formed, if they come from the combination of a translation and a vibration, or if they come from a combination of two rotations. And then that photon, or those two photons, then need to be rotated again in 3 dimensions. Again, space, time, and motion have 3 dimensions. When you're talking about coordinate space and coordinate time, those are 3 dimensions of space and 3 dimensions of time, respectively. But each one of them only occupies 1 dimension of motion. It takes 3 dimensions of space to describe 1 dimension of motion. But you have 3 dimensions of scalar motion. So if you are to rotate a photon or 2 photons, they have to be done in 3 dimensions. And that's why in Larson's periodic table, he has 3 numbers. The first number is the first 2-dimensional rotation. The second number is the second 2-dimensional rotations, and they alternate. And then the third number is a 1-dimensional oppositely directed rotation, which can be 0 in the noble gases, and it can be positive or negative. And so that is what Larson starts with. Those are the numbers that he starts with when he builds up his equations. Now, in the time region and in the space region too, the solid state is established on an equilibrium where the force of gravity and the force of the progression are equal. And that is how you get this interatomic equilibrium. The distance that is established between atoms is established at that spot where the force of gravitation, which is variable, is equivalent to the force of the progression, which is inward and which is constant at the speed of light in all directions. And then compression is from 2 factors. One is this internal pressure from the progression that's moving everything closer together. That is what he calls an internal pressure. And then there can be an external pressure if there is some force that is also progressing that matter. And so those 2 things have to be added together and taken into account as you try to measure the compression or the compressibility, which is the rate of compression. Okay, we'll see where Larson goes here. We're in the middle of this chapter, which we have been for several days. And we're just trying to creep our way through this. It's very difficult going. I'll try to explain what I can understand, and that's why I try to explain and read this verbatim, because I don't understand it to a 100% comprehension rate. I'd probably get 70 or something like that. But when I first read it the first time, I would have gotten a 5. So, you can really improve, but you have to kind of get the basic gist and then, do detective work and try to piece together what you can from there. But you got to cut Larson some slack, because he's, the first person that's writing about this. And so he's having to come up with a new language, new terminology, and he's having to cover all the bases. So you got to really read it carefully or read it multiple times. Okay, as in the compression of the elements, the theoretical calculations do not always confirm the transitions reported by the experimenters. On the other hand, these calculations show that a large proportion of compounds, including 6 of the 8 in Table 17, undergo either a transition or some other process in which they eliminate a volume component in the pressure range below 5,000 kilograms per square centimeter. The effect on the compression curve is to cause the linear segment of the curve to intersect the zero pressure ordinate at a volume below 1. The origin of these volume adjustments is still uncertain. The occurrence of a number of observable first-order transitions at relatively low pressures suggests that some early second-order transitions may also be taking place. Again, the second-order transition is a transition of the compression factors. More and more compression factors are being brought to bear to resist the pressure. Compression factor is really part of the rotation of the atom, which is the gravitational rotations. And, those are the 3 numbers of the periodic table, more or less. He alters them in certain ways, but more or less. And then, but pressure is 2-dimensional, whereas the volume is 3-dimensional. So the amount of pressure that is applied is dependent upon the orientation of the atom. And so when just a little pressure is applied, the atom doesn't really adjust its orientation to adjust to the pressure. But as more and more pressure is applied, then the atom needs to bring all of its rotational forces into play to resist that pressure. So that causes transitions. At certain points, more and more of the rotational factors are brought to bear to resist the compression. And so that creates basically inflection points in the curve of the compressibility. That's called a second-order transition, while a first-order transition is the result of the crystal structure, or the lattice, the crystal lattice of the atomic configuration. A change in that also can cause the curve to inflect like that. Okay. The origin of these volume adjustments is still uncertain. The occurrence of a number of observable first-order transitions at relatively low pressures suggests that some early second-order transitions may also be taking place. But it is also possible that voids in the structure may be eliminated in the early stages of compression, or that there are geometrical readjustments. The structural characteristics of the organic compounds make them particularly susceptible to such geometrical readjustments. Because of their low melting points, their volumes under low pressure also include the additional component that exists near the change of state. It appears, however, that in a wide range of compounds, elimination of these extra volume components is substantially complete at some pressure well below the 40,000 kilogram per square centimeter level to which Bridgman's measurements on solid organic compounds were carried. This means that there is a fairly wide pressure range in which these compounds follow the normal compression pattern. The following comparison of theoretical and observed volume ratios for benzene and some of the polynuclear derivatives give an indication of how the elimination of the excess volume progresses. A measured ratio lower than the theoretical means that some of the excess volume is eliminated in the pressure range for which the ratio is measured, and the amount of the difference is an indication of the amount by which the normal loss of volume due to compression is increased. Okay, so come upon a table here. Looks like he is first talking about benzene, and he gives really just the ratio of pressures. It looks like the kind of reference pressure is 40,000, but I thought that the capital M was a million, but 40,000 kilograms per square centimeter. And again, that is the pressure. Pressure is force per area. In Larson's system, pressure is time over space to the fourth power. Force is time over space to the second power. And then area is space to the second power. But in the MKS system, force is pressure is force per area, and that's why he's saying, I believe that's why he says that pressure is two-dimensional, whereas the volume is three-dimensional, because it's on an area. Although you can also say that pressure is energy per volume, because energy is time over space, and volume is space to the third power. So pressure is also energy per volume, but we're not looking at the energy, I guess. We're looking at the force. And so the force is a two-dimensional, force, and the pressure is two-dimensional, whereas the volume is three-dimensional. Anyway, the reference volume is 40, and then he's looking at measurements here of 20, 25, 30, and 35, and he's actually not particularly close here with his calculated values. Observed is 0.938, calculated is 0.920. Observed for 40 to 25 is 0.954, calculated is 0.943. 40 to 30, observed 0.970, calculated 0.964. And then he actually is close on the 40 to 35, 0.985 as opposed to 0.984. Now, when he's dealing with, I'm trying to kind of analyze this diagram or this chart here, this table. Looks like I'm not sure what those values refer to. I thought they were referring to benzene, but now he's talking about naphthalene and anthracene as well. In any case, maybe he'll explain it. As these figures indicate, benzene is just getting rid of the last of the excess volume at the pressure limit of the experiments, and there is no linear section of the benzene compression curve on which the slope can be measured for comparison with the theoretical value. With increased molecular complexity, however, the linear section of the curve lengthens. And for compounds with characteristics similar to that of anthracene, there is a 15,000 kilogram per square centimeter interval in which the measured volumes should follow the theoretical line. Compounds of this nature have magnetic rotation 3,3. Those are the first two numbers of the periodic table for Larson. And electric rotation 4. So that's basically he's using compounds. Sorry about that. Basically he's using compounds, but he's using their equivalents in for an element or for a single atom. 334 for the electric rotation. The effective value of sulfur trioxide, I guess, is therefore 0.812, where the compression factors are 4, 1.5, 1. Those are the compression factors. Those are the factors that are brought to bear against the pressure. The resulting internal pressure is 127.2 I guess 1,000 kilograms per square centimeter, as shown in the values tabulated for benzene, which were computed on the basis of this internal pressure. The ratio of the volume at 40,000 kilograms per square centimeter to that of 25,000 should be 0.954 for all organic compounds with characteristics such as molecular complexity, melting point, compression factors, etc., similar to those of anthracene. Table 18 shows that this theoretical conclusion is corroborated by Bridgman's measurements. And Bridgman was one of the original investigators of this and one of the giants of early 20th century physics, I guess. And, or maybe chemistry. And so he's looking for this 0.954, and it looks like, you know, with a bunch of these different compounds, including nitrurea, cyanamide, xylene, chlorobenzoic acid, bromobenzoic acid. They're all 9.954, or in a couple cases 0.956, 0.953. And yeah, so it looks like at the time, the theoretical values listed in the foregoing tables were originally calculated. Bridgman's results constituted almost the whole of the experimental data then available in the high pressure range, and his experimental limit at 100,000 was the boundary of the empirical knowledge of the effect of high pressure. In the meantime, the development of shockwave techniques by American and Russian investigators has enabled measuring compressions at pressures up to several million atmospheres. Now, I don't like the way he switches from this kilograms per square centimeter to atmospheres, but I believe they are either the same or very, very close to the same. He did mention it earlier in the chapter. Okay, with the benefit of these new measurements, we are now able to extend the correlation between theory and experiment into the region at the maximum compression factors. Okay, so I guess from here, we're going to be going into an area where he's looking at very, very high compression. And at that point, like, all of the compression factors of the atom are going to be brought to bear. So we'll get into that tomorrow. Don't get discouraged if you're getting confused. You know, this is just to kind of see how Larson thinks. Just try to get the basics, and you can build from there. Have a great day.